we go. Hi, everybody. I had my window on the wrong screen and I got confused, even though I was literally clicking on it. Welcome back to Chem 140. I hope everyone had a good Halloween. I did. I slept 14 hours. Because I went and got my vaccine booster, because I am a teacher, and teachers need to be vaccinated like crazy. So they sent me an email like, hey, it's been 6 months. Do you want to do this? And I was like, absolutely. When can I do it? And they said, Halloween's Eve. And I was like, okay. I wasn't going to do it on Monday because then I don't know what I would have been like tomorrow. So I got it, and basically the side effects that I have had from the vaccine are I get real tired. I'm a lucky one, apparently. Like, I know a bunch of people, when they got vaccinated, they were, like, sore and couldn't do anything and got the, like, crazy fever or chills. And, not me. No, I had a few chills, but mostly just tired. So, I'm feeling better now. Go get vaccinated if you haven't, as long as you're eligible. Today, we are going to do Unit 10. We're going to do pretty much everything in Unit 10 today. And we might even start Unit 11 if we have time. I did overlap with my party because I went to a party on Saturday evening. I went for an hour and a half. I was like, that's enough social life for me, you know, after 2.5 years of not seeing anybody because of the pandemic. Yeah, if you have a question about the schedule for winter quarter, I realized it just went online. And I did look at it. There are some issues with it. So, CCN, I actually don't know what that means. I saw that was listed on a bunch of things. I think that you can, I want to say it's like corrected course numbers or something like that. I'm not 100% sure. You can ignore the CCN designation. There's only one field, it's Chemistry CCN. That's the one you want. All of the instructors and the sections they're listing are correct. I checked mine, and it does have me listed for the classes that I was told I was going to be teaching. It does this weird thing where it split the lab and the lecture apart, and it seems to have listed both of them as credit. You're not signing up for 10 credits all of a sudden. We did not suddenly make chemistry 10 credit classes. So ignore the credits for any section that has the L as the last character. So, like, if it says LS1L, that means live stream 1 lab. And the L doesn't have credits associated with it. Or it will, but it'll be 1.5 instead of 1, or 5, or whatever. That'll get fixed. We just emailed the dean about that, and she's looking into it. No, I'm not teaching 161. The classes that I teach each quarter are assigned, sort of, to me. The way that it works is that we have a bunch of classes, and then everybody picks some, and then I'm towards the end, and I just pick whatever's left. Mostly because I don't really have a preference. I teach whatever. I teach all the classes, all the way up through 163. And I would teach 261 if they asked me to, but everybody wants to teach that, so. Who do I recommend to take 161 with? I would honestly say take anybody. I saw Valerie up there. I saw Mark up there for 161. They're both great. I think that it's going to come down to, like, whether you want to do OL, which is just online, where everything is... It'd be like where we don't have these live streams. They just automatically get posted, and then all the sections are question and answer / practice sessions where you just go in and work problems and stuff. Or if you want to do LS, which is closer to what I think I'm doing, though I think Mark does his own thing. So you'd have to ask him, like, hey, what do you do? And he might be able to give you that information if you particularly care. Agenda items before we get started. Lab worksheet number 3 is due this week. It's due Wednesday. Make sure to get that in before the deadline. It closes on the 4th, and the 4th is my birthday. I will be 38. Yay. Alright, let's get started. Let's talk about covalent compounds. We spent a long time in Unit 9, a long time being a whole week, talking about ionic compounds. And we talked about how they are substances that are composed of ions that then attract to each other and form a lattice, which is crystalline. Oh, I got it. My tablet, or not my tablet, but my stylus here. So, ionic compounds are crystalline. Do I know of any in-person chemistry classes next quarter? Not in our department in 161. Anything that's in person will not say OL or LS. It'll just say A or B. Like, I know we're doing organic in person now. And I think in spring that'll probably change. For me, it's dependent on the labs. Labs are currently capped at 18, and the class holds 25. So I'm not doing labs until in person until I can get everybody in there. That's just how I feel like what I'm going to do. Oh, I'm strontium years old? Ooh. Yeah, I'm working my way down the periodic table pretty quickly, I have to say. Hey, if I make it to uranium, I'll be happy. My grandfather made it to uranium. I think he was like 95, 96 or something like that. So, longevity runs in my family, I guess. Hopefully. Alright, so we talked about ionic compounds. Ionic compounds are crystalline. And they also have really, really, really high melting points. So, it turns out that if you try and melt an ionic compound, like table salt, you have to heat it up like crazy hot, like 800, 900 degrees. Now, all of that being said, there are substances out there that melt way, way lower. For example, water. Water melts at 32 Fahrenheit. You put it in the freezer and it turns into a solid, but you bring it out and it will melt pretty quickly, right? Excuse me. And water is not crystalline at all at room temperature. In fact, other covalent compounds like sugar, if you like grind sugar up, you don't get a crystalline substance. You get this sort of powder. For example, powdered sugar. You've probably bought or had that on like a dessert or something like that. You've seen it before. It's very fine. Way finer than anything you can get with like salt. Even popcorn salt, which is like really, really fine, it's still kind of crunchy looking and crunchy feeling. So there are substances out there that don't act and behave like ionic compounds. Those are our covalent compounds. And so the conclusion that we draw examining these compounds is that, well, if we're going to look at the bonding, and the bonding sort of dictates like macroscopically what we examine them, or how we examine them. Would the bonding in covalent compounds be unique? Or would it be similar? How would the bonding be? And it turns out that the method of how things bond in covalent compounds is similar in terms of like what we're going to do. So like the octet rule still applies. But in terms of like how we draw structures and how we move electrons around and do we transfer them, there's a lot of differences. And that's what we're going to explore in Unit 10 here. We're going to do this really briefly. We're just going to talk about Lewis structures, really. And then in 161, you're going to talk about covalent compounds in a lot more detail. You'll talk about polarity and electronegativity and all that stuff. We're going to just ignore it for now. We just want to draw the structures so that when you get to 161, you can draw them. It looks like my connection is okay. Is your screen really blurry? If your screen is blurry, there should be a button. Let me see if I can... It's like over... Let me see if I can do this. So, like, way over here, there's, like, something that looks like a gear. That's my attempt to draw that. If you hover over the picture. And if you pick the picture and pick quality, you can change the playback quality. Set it to something higher. If it's playing, like, at 360, then you won't be able to see it. Set it to 720 or 1080. And that should fix it. If that's the issue. Alright, so let's talk about how we find structures in covalent compounds. So we want to get octets. So octets are still our goal. We're going to try and get to 8 electrons around every atom involved with 1 or 2 exceptions. We'll talk about those. However, we're not going to transfer electrons anymore. We're not going to do this. So we're not going to have, say, A and B here. I'm just going to draw some electrons quickly. So this is what we did for ionic compounds. We'd move one over, and then A would have no electrons around it in its valence shell, and then B would have an octet, and then they would attract together. This is ionic. And we're not going to do that anymore. Instead, what we're going to do is we're going to share electrons in a specific way. And well, I'll show you what I mean by that on the next slide here. Now, anything that shares electrons in the way that we're going to show it forms what's called a covalent bond, and we're going to call it a covalent compound. You might have noticed the word valent in here, implying, oh, we're going to use valence electrons again. Yeah, we are. But what does co mean? It means communal. The electrons are going to be put in a pool, and then everybody gets to use those electrons. Everyone shares the electrons together. So the first example that we're going to do is fluorine. And if I were to draw the Lewis structure for fluorine, I'd go to the periodic table, and I would say, oh, well, it's in group 17, so it has 7 valence electrons. Hopefully we remember that. And there we go. So there's a fluorine. And now it's F2, so I'm going to draw a second one. Oops, I should probably draw the whole F here. There we go. And you'll notice that if we were trying to treat this like ionic, where we moved electrons over, there is no way that I can move electrons and give everyone an octet. It's just not possible. If I move this electron over, then the fluorine on the right would have an octet, but the fluorine on the left would not. It would only have 6. It'd be further away from its octet. So we can't just move electrons from one atom to another. We have to do something different. And so that's something different that we're going to do is we're going to cheat. Now, atoms are dumb. They don't have brains, so they don't know that they are actually being cheated out of electrons. But what we can do is if I push them close enough together like this, you can see they kind of fit together like a jigsaw. Those unpaired electrons go into the same space between the two atoms. And now what I can do is I can say, okay, well, how many electrons does this fluorine have on the left? Well, I'm going to circle them. There's 8, and it has an octet. Now, how many electrons would the fluorine on the right have? Notice that I'm circling the same 2 that are in the bond as on the red side. We're just double counting them. How I put the electrons in is just, I'm trying to do it 1 per side, and it doesn't really matter where you put the unpaired one. I'm trying to put the unpaired ones in a place that it helps me. Like, I knew I was going to bond them together, so I put the unpaired ones in the middle there, like so. Remember that you want to put your electrons on your atom 1 at a time, 1 per side. And then once you have 1 on each side, you start pairing them again. Now, sometimes you might see me draw them like this. Oops, that's the highlighter. You might just see me really quickly go do, or whatever. Don't do that. That's just, I get permission to do that because I've been doing this for 20 years. When you're learning, you want to do it 1 per side, and then pair them. So there are our octets for F2. And I've made them by double counting the ones in the middle, particularly the ones in the center of this Venn diagram type illustration that I've drawn here. Oh, I don't know why that went back. There we go. So you can see that in the boxes, each atom has an octet. So we're all set. Your goal when drawing substances that have covalent compounds is to arrange them such that the unpaired electrons, these 2 electrons were the ones that were formerly unpaired. And so we're going to pair the unpaireds together, and those will make our covalent bond. Well, there you go. Now, what we're going to do is we're not going to put dots between atoms because it gets a little cumbersome to have to count dots. So later on, well, not really later on, we're actually going to start doing that now. I don't know why there's a little underscore here. But later on, what we're going to do is we're going to replace... Oh my goodness, my computer's being silly. We're going to replace the dots that were here. So this was 2 dots here. We're going to replace that with this line. And the line is going to represent our single bond. So whenever you put 2 atoms together, any pairs of dots that you have between 2 atoms, erase them and replace them with a line. And that's how you get your bond. Now, what are these guys on the sides? Do they make bonds? Well, they don't because they aren't between 2 atoms. We're going to call them non-bonding pairs. These were the previously paired electrons on our atoms. They don't do anything. They've already been paired. They don't need to interact with anything. They just hang out. So whenever you are drawing Lewis structures, you're going to look for the unpaireds and use them to make bonds. Anything that's paired already stays a non-bonding pair. That's why when you're drawing an atom, you want to do 1 electron per side. So if I was looking at oxygen, these would be my non-bonding pairs. And then the single ones, right here and right here, these would form bonds to other atoms. All right. So really this comes down to, can you write the Lewis symbol for any atom? And yeah, you can. We did that in Unit 9, right? Then you just have to put the pieces together like a puzzle. This is going to be our easy way of putting molecules together to make a structure. Now, this is going to work for very, very simple molecules, but as we increase the complexity, the method sort of becomes cumbersome. So we're going to stick with this for this first example, and I'm going to have you try and build some on your own. And then we're going to do a different technique that's more complex to deal with more complex molecules. So while we're doing this, let's remember some ideas here. So whenever you draw a line, remember that the line represents the 2 electrons that are between your 2 atoms. You would then replace it with a line. So we'll say line goes here. Now, when you see that, so for example, if you saw something that looked like this, and you were checking your structure to say, is it an octet? Excuse me. Does it have an octet? Well, when I circle my atom and I count my electrons, I would go 1, 2, 3, 4, 5, 6. And remember, a line counts as 2. So each line counts as 2 electrons. So you'd say, yes, A has an octet. So this is just for checking your structure. Now, not all atoms will actually get to 8. Nearly all of them will. There is one exception, and that exception is hydrogen. Hydrogen is too tiny to have 8 electrons. Hydrogen starts like this. And so all it can really manage is because there's only 1 proton there. 1 proton is not strong enough to attract 8 electrons to it. At most, our hydrogen atom can take up to 2. And the reason for that has to do with, well, how does the octet rule work? We're landing on things that look like noble gases, right? When I add or discard electrons, the end result is I now have as many electrons as a noble gas, right? That's how we've been doing this all along. With hydrogen, the nearest noble gas is helium. And so we're just going to add one electron to it from something else, say like another H or whatever, and then we're all set. So hydrogen's the weird exception. It only needs 2 electrons, which means that you just need to stick your hydrogen as a bond to some other atom, and then it will be satisfied. Everything else will need 8, so we'll have to achieve the octet rule for all other atoms. Now, can you share multiple electrons? Sure, you can share as many as electrons as you need to with one atom to get to an octet. Now, there are some considerations that we have to worry about. I'll show that in just a second. So let's look at first oxygen. So here's what oxygen looks like. It has 6 valence electrons. And I'm going to put another oxygen atom next to it with 6 electrons. Why 6 valence electrons? It's in group 16. And now how does everything get an octet? Well, if I were to pair these two, I could form a bond. But I could also pair these two as well, right? Am I allowed to make 2 bonds to the same atom? Sure, why not? So if I do that, and I rearrange, now I have 2 pairs of 2. Well, we said that we had a line for every 2 electrons. We'll just draw 2 lines. And so I've made a double bond. So you can have as many bonds as you want, as long as you have unpaired electrons to work with. For example, if I did nitrogen here, nitrogen looks like this. And N2 is a common gas. If you take a deep breath, you're breathing mostly N2. I'm going to just share these guys, and these, and these. And then I get N2. Now, can I do 4? What if I took carbon? We're just kind of going across the top row here, right? What does carbon look like? Carbon, maybe we could make 4 bonds out of it, right? So if I pair these one, oops. If my tablet doesn't move, oh no, no, why did it all go away? Oh, there we go. I hit the wrong button. All right. So if I pair where's my cursor? There it is. If I pair these 2 together, and these 2 together, and these, there's my triple bond. Let me try and pair the 4th one together. Oh, well, I can't go through the nucleus, right? I can't make a bond go through the nucleus because there's already stuff there, right? And I can't like go around, right? So I run into this issue of, oh, these guys are on opposite sides and they only go like that. I can't make a bond going around like this. I can't do this sort of thing. That's not allowed. So in our structures, the most that we're going to be making between any 2 atoms is 3 bonds, and that has to do with geometry. We just can't get the 4th electron to stretch itself around because it's already pointed in the wrong direction. And so in this case, what our structure would end up looking like would be, here's my triple bond, and then I have another unpaired electron, and this can go to some other atom like that. So 3 bonds max. Between 2 atoms. And I'm going to put a little asterisk here in this class. If you get to 300 level chemistry, this falls apart because transition metals, again, are strange. All right. So we already did the example here for nitrogen. I did the Lewis structure for nitrogen. We'll just put it on the previous page. I'm going to put the other Lewis structures here. I'm just drawing them in real quick. And then we did F2. Now, it turns out there is a pattern to the number of bonds that each atom wants to make. And that pattern matches up with the number of unpaired electrons each atom has. Now, this isn't the number of bonds necessarily to one other atom. This is the number of bonds total it will make. And those patterns follow this formula down here. The number of bonds is 8 minus the group number, but just the ones digit. So 7, 6, 5, or 4. So and again, that has to do with, so I'll draw Cl here, for example. So Cl only has one unpaired electron, so my bond would occur here. Whereas something in group 6A or 16, such as sulfur, I would form 2 bonds and they'd go here and here. And so on and so forth. This pattern is going to be good enough for our purposes for this class. And if there's something that doesn't follow these rules, and there are, of course, exceptions, we'll talk about that when we get there. You're going to see all sorts of exceptions to this in 161. All right, so what I want you to do is I want you to try and draw the Lewis structures of these molecules by following this pattern of drawing out the Lewis symbol for each of the atoms. So here's my Cl, and here's my Cl for Cl2. And then how do you connect the unpaireds? Well, I could just do this one. There you go. So I did the first one for you. Do the same thing for BRF, CF4, H2O, OF2, and then down at the bottom, C2H4 is a little tricky. And I'll give you a hint. The C's are connected to each other, and the H's go along the outside. Remember, H can only connect to one thing. Okay? Try drawing these. And when we get back, we will go over the answers together. Okay? We'll give you about 5 or 6 minutes. Obviously, you can't type this into the chat box unless you're really good at like ASCII art, which nobody does anymore. So just say done or something like that. All right, see you in a bit. All right, one more minute and we'll go over the answers here. All right, so let me put this up on the screen. Okay, we already did Cl2. You could see that. So let's do the rest of these. All right, so let's do BRF, also known as BERF or BARF. I don't know. All right, so we got bromine, which has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. There we go. And we got fluorine, which also has 7 valence electrons. And then we're going to just pair the unpaired together. So, whoop, there you go. So there's our structure for BRF. All right, what do we got next? We got CF4. So I've got a bunch of fluorines here. I got to make their dots a little bigger. Let me make the pixel a little bigger. Why aren't you? That's too big. I gotta type it in here, so we'll just do that. Okay. So we got fluorine. Oops, I drew it the fast way. Let me draw them the correct way. Just so we don't end up in a do as I say, not as I do situation. Let me make these a little bigger here. There we go. And then I got a carbon. Now, you could say, well, I'm just going to draw all of my connections together here. But this is not a Lewis structure. This is kind of gross, right? So we need to tidy up. But you could do this as a blueprint to say, oh, these are where my connections are going to go. I'm going to connect the unpaireds. And so what you would end up having when you were done would be something that looks like this. And yes, you do have to draw all the dots. The dots are part of the Lewis structure. I know that's obnoxious, but we do have to include them because we need to know where the non-bonding pairs go. This will be important in 161 when we talk about space and geometry and like electrons taking up space, even though it doesn't look like there's an atom there, because there isn't. It's just electrons. So there's CF4. You do H2O. H2O is pretty simple, and you've already probably seen the Lewis structure for H2O already. There's H, there's O. And then I'm going to connect the unpaired, so I'm going to connect these two together and these two together. And then we'll tidy up. So there were those, and then I've got like that. There you go. There's my H2O. Now, can you draw this in some other orientation? Well, sure, if you take the little select tool. You just spin it around however you want to, right? So I could just do this. There you go. So that's correct. That would be correct, too. You could do whatever you want. Any orientation is fine, right? Oops. It's going to yell at me until I do that. There we go. So that's sort of a joke. I mean, I can do that. You can't do that with your paper. But a better question would be, what if I did this? And as long as you draw the electrons in, yeah, sure, that's fine. Because remember, you can have your oxygen be like this, yeah? This is allowed as long as you have 2 pairs and 2 unpaireds. Then that's allowed. And then you could put your H's on both sides. So both of those structures are legal. Okay? All right, what else do we got? We have OF2. I've run out of space, so I got to scroll back to the top and hit clear. So we'll just trash everything. So we got OF2. So here's my O. And I got an F. And then I've got another F. I just heard my cat opening a cabinet. And I know she's not supposed to be in that cabinet. Maya! Maya, don't. She's in the bathroom. My cat has discovered that she can open any cabinet she wants to. And most cabinets I don't want her to. So we could do something like that and something like that. I really shouldn't put an arrow because we're not transferring electrons. We're just connecting these. So again, pair the unpaireds. And then we'll tidy up. So I'll have my O. Line, F. And then the other F. There you go. There's the Lewis structure for OF2. It looks just like water, except instead of hydrogen, it's got fluorine. Don't drink it. It's toxic and awful. And then this last one down here for C2H4, how do I put all these pieces together? So H, 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 H. And I got C, and I got C. And so this is sort of where this method kind of falls apart, because there's a lot of things that you could try and do, and it would end up kind of miserable. We have to pair all the electrons together, so you can't have leftover electrons. So if I ended up with a structure like this, for example, if I did something like this, this is no good. And the reason that it's no good is because, well, I didn't pair all the electrons, right? So I have to pair all the electrons. They have to form, the single electrons have to form bonds. So what does that leave for us to do here? Well, if I do this, so if I connect my H's to my molecule, I do 2 per carbon, then that leaves me these guys that I can then connect together. And so what does that look like when it's done? Well, I have a double bond between my C's, so I'm going to write that. And then I have 2 H's coming out each side. All right. So that's the correct answer for C2H4. This is called ethylene or ethene. The proper name is ethene, but nobody calls it that. It's ethylene. And drawing that structure using this method, you can see it's kind of obnoxious, right? Because you just have so many pieces. We're going to be working with molecules later that have lots of pieces. And drawing all of the atoms individually and then trying to do this connect the dots, it looks like a football diagram. Like, it gets convoluted really quickly. So we're going to need to devise a better method that helps us get to the structure without having to deal with playing connect the dots all the time, okay? So we're going to do that in this next section. But before we do that, since it's a good time for it, we're going to take our break a little bit early. I'm going to go scare the cat out of the cabinet with the compressed air because that scares her. I had to do that with her in the sink, unfortunately. So let me put the timer up real quick. And then, oops, no, of course, I don't want to update. We'll start this. We'll get the music going for Cultist Simulator again. And I'll see you in a bit. Oops, guess who didn't unmute the music? I'm the worst. I went back to check on this, and I noticed that the music was muted. I was like, oh, I can hear it just fine. Yeah, but you guys can't. So that's too bad. I mean, I could just do Cultist Simulator music tomorrow, I guess. Whatever. Alright, so, welcome back. Hope you had a nice, quiet break, because I accidentally didn't hit a button. What we're going to do now is we're going to try and draw bigger molecules where the connect the dots method doesn't quite work. And so you don't have to do connect the dots anymore. What we have done so far this period isn't worthless. It's just sort of to get you in the idea of like, okay, this is what my structure should look like when they're done. So if you were able to do them so far, then great. You're where you need to be. Now what we're going to do is we're going to apply a different methodology that will get us the same structure, but will work for more complicated structures. All right, so we're going to do a 5-step plan here to draw a Lewis structure. Now, this 5-step plan is very important that you, 1, do all the steps, and 2, do them in the order that they're presented in. Once you go to the next step, you cannot backtrack to the previous step. There will be some instances where you'll get to a step and you'll be like, oh, I can't do it. There's nothing to do. Then you just go to the next step. And if it becomes possible to do it at that point, you don't return. So make sure you do all the steps in this order and do them conditionally. Can I do this now? Okay, I'll do it. If not, we go to the next step. And that's fine. Okay? So I'm going to talk about the steps real quick, but then we're going to do an example where it will contextualize all these steps. So if this sort of goes over your head, don't worry about it. We'll go over the steps, we'll do a molecule, and then we'll go over the steps again and show what we did. Okay? So the first step is to take your molecule, and we're going to count all its valence electrons. Remember that in covalent bonding, we care only about valence electrons. We're just going to tally them all together. Once we've added all the covalent electrons together, we'll just put them in a pool. We'll say, oh, I have 12 electrons to play with, or 20, or 28, or whatever. Then what we're going to do is we're going to draw what I call a framework. Basically, what this means is that I'm going to take the atoms that was given to me for my formula. I'm going to try and connect them together in a rudimentary way. Every time I draw a line to connect my atoms, I'm going to use up 2 of my electrons from the count up here that I had. So basically, I'm doing this in reverse from how we did it. I'm just going to put down letter symbols and then draw lines between them. Now, the formula is written in such a way that the first element goes in the center. Okay? So if the formula you're given is this, which is our example that we're going to do, you would put carbon in the center because it's the first labeled element, right? Then you'd put the oxygens around the outside. So I'd go like something like this and then draw lines together. And that would be my framework. What if I instead had something like this? Well, again, carbon is listed first, so it goes in the center. And then I just put everything else around it. And I go do. And there's your framework, okay? So your framework is going to be, write whatever atom was written first in the formula, put it in the middle, and then put everything else around it. All right. Now, there is one exception to this. If you have H as the first element, use the second element in the center. H can never be a central atom because it can only connect to one thing. So H is forever consigned to be on the outside. Now, what if you have multiple of the first atom, like C2H4? In that case, try and keep that the carbons as central as you can. This will not always be possible, but 99% of the time, and for all the examples we do in this class, it will work. All right. So that's step 2, draw the framework. Step 3, we're going to put in all the dots, and we're going to put dots for our electrons. We're going to put this on, so the language that I wrote here is put electrons around atoms bonded to the central atom. In other words, we're going to do the outside atoms first. That's step 3. Step 4 is put the leftover electrons on the central atom. So central atom is last. So do the outer atoms first, then do the central atom last. And then finally, step 5 is if you ran out of electrons and you need more for the central atom, then and only then do you make multiple bonds. And we'll show you what that means in a second. Hi, you're a cat. Hi. Kresnik is here. He wants to say hi. Oh, no, he doesn't. He wants to run away. I don't know where Maya is. She's probably in the living room, sitting on the floor. Or on the kitchen counter. Now, even though there are 5 steps, if at any point you get an octet for everything, excluding hydrogen, hydrogen only needs 2. If at any point you get an octet for all atoms, then just stop where you're at, and your Lewis structure is done. You do not need to do the remaining steps. So you can finish as early as step 2. Maybe you only need to do the framework and just connect everything. But you might end up stopping at any point along this process. And as long as you have achieved these conditions, your Lewis structure is complete. So what we're going to do now is apply these steps to CO2. And my slides walk through them, but I'm going to do this on the Photoshop canvas anyway. So let's see here. Oops. Well, oh, I blew it up. That's what I did. Okay. I was holding the wrong button. Wow, I've really screwed this up, haven't I? Hold on. Okay, there we go. That's good now. All right, so I'm going to write out the steps one at a time. So step 1 was count valence electrons. We're going to do that over here. So carbon dioxide, CO2, we're going to count each atom's valence electrons individually. So how many valence electrons does carbon give you? Well, if this is what carbon looks like, there are 4, right? And then each oxygen, well, if I draw out the oxygen, each of them has 6. Well, there's 2 of them. So each would have 6 electrons. And then I add everything together. Now, you don't have to do this step every time. You could just go to the periodic table and say, oh, it's in group 14, it has 4. Oh, it's in group 16, it has 6, and so on and so forth. So 4 plus 6 times 2 is 16. So we have 16 electrons to work with when drawing the structure of CO2. Okay? All right, so that was step 1. Step 2 is the framework. And we said that the central atom is the first one listed. So because CO2 has carbon first, I'm going to put carbon in the center. And I'm going to put the oxygens around it. And then I'm going to bond them. So there's my framework. But remember what we said. Each time you draw a line, lines represent 2 electrons. So I need to pay for these electrons. So here were 2 in this line. Here were 2 in this line. So 16 minus 4 is 12. So I've used 4, and I have 12 that are unassigned. That was step 2. Step 3 was to put electrons around the outer atoms first. So I'm going to do that. Now, when you're assigning electrons from your pool to give them to the outer atoms, just put the dots down. You don't have to do one at a time. Just do this until you have an octet. So there's my octet, because I have 1, 2, 3, 4, 5, 6, and a line makes 8. So this oxygen has an octet. That cost me 6 electrons to do. So we'll pay for them. 12 minus 6 is 6. Okay, let's do the last oxygen over here. 1, 2, 3, 4, 5, 6. That one's a little small. Let me make it bigger. Okay, I got to pay for those too. All right, I'm out of electrons. All my electrons are used up. And I have octets on the outer atoms, but now when we get to step 4... Oops, that's not what I want to write. I want to write... Step 4, put the electrons that are left over on the central atom. You'll notice that, well, I don't have any, right? So I can't do step 4, so we move on to step 5. And step 5 is, well, make multiple bonds if the central atom doesn't have an octet. Well, it doesn't. It only has 4 electrons here, right? So I only have 4 of the 8 that I need so far. So what we're going to do is we're going to make multiple bonds. And the way that you make multiple bonds is that you take electrons and you remove them as a pair and you make them a bond. So I'm going to go erase. And I'm going to make them a bond. So now oxygen still has an octet, right? Because it's got 1, 2, 3, 4 dots, and then 2 lines. Each of those lines is 2 electrons for a total of 8. So this oxygen still has an octet. But now when I look at carbon, it's got 3 lines coming out of it instead of 2. So instead of 4 electrons in its octet, it now has 6. So we're actually closer, but we're not quite there, right? So I'm going to do the same thing on the other side. I'm going to get rid of these electrons, boop, and I'm going to put them in the bond right there. The oxygen on the right still has an octet, but now carbon in the middle has 4 lines coming out of it. It has all 8 of its electrons. And so it now has an octet too. This is the correct structure. Now, some things that you'll notice that before we got to the finished structure, we had some weird looking things. Like oxygen had 3 pairs of electrons around it, but that's not something that we can do, right? Also, oxygen only was bonded to one thing midway through the structure. That's fine. Remember the little rules that we talked about before, how oxygen likes to bond to 2 things? That's going to apply to the finished structure and not necessarily to anything on the way to the finished structure. So if you're putting down electrons around your outer octets and you realize, well, wait a second, this looks weird, that's probably because you're going to adjust it at the end. Okay? So follow these 5 rules in this order. And when you get to the end structure, you will have the correct Lewis structure. It might look weird along the way, but when you get to the end, if you're following the rules correctly, you will have the correct structure. All right, so now my slides just walk you through this. And there you go. All right, so let's do another example. I want you to draw the Lewis structure for ammonia. So I'm going to let you try to do this. I'll give you 2 minutes. Follow all the steps, all 5 steps. So count the valence electrons, draw the framework, place the electrons on the outside atoms first to fill their octet, then the central atom, and then make multiple bonds if you have to. Okay? I'm giving you sort of simple molecules that you could still use the connect the dots method, but do try to use the 5-step plan. Okay? I'll give you about 2 minutes, like I said, and I'll come back and we'll go over the answers. One more minute, we'll go over the answers. All right. So let's do the 5-step plan here. If I can find my cursor. There it is. So step 1 is to count electrons. I can't spell. And so nitrogen is in group 15. Therefore, it has 5 valence electrons. Hydrogen is in group 1. It has 1 valence electron, but there are 3 of them. So there are 8 electrons total. Step 2 is our framework. So I got nitrogen, I got hydrogen, hydrogen, hydrogen. I'm just going to put the nitrogen in the middle. Hydrogen's around it. I'm going to connect them all. 1, 2, 3. I got to pay for those electrons. So 8 minus 6. Each line is 2. 2, 4, 6. Okay. What if it doesn't add up to a multiple of 8? It might not. And it turns up that that's okay, because remember, you're sharing electrons, so you could get any manner of weird things. These examples that we've done have landed on 8 and 16. The only thing that is required is it must be an even number. If you get an odd number, you've made a math error, okay? Because you can't have everything be paired if it's not even. So outer octets, well, I got hydrogens, so those don't get any more electrons. Oops, central octets. You'll notice I keep writing inner octets, and that's because later on in 161, we're going to have multiple inner atoms. So there's where my last 2 electrons go. And then 5 is multiple bonds. And I don't need to. Everything has an octet. Well, nitrogen does anyway. So there you go. This is what your structure should look like. Now, if you have some other little angles, so like everything's right angles, that's fine. In fact, if I push the button, it looks like this, where it's all right angles. I'm going to hit clear so you can see that. Totally fine. The orientation doesn't matter. So if yours was like this instead, totally okay. All right, so now what I want you to do is I want you to try using the 5-step approach for these molecules. Remember, what I list first is always the central atom. Now down here, I start throwing in multiple central atoms. When you get to these situations, remember that you're going to stick your central atoms in the middle, and then you're going to put stuff around the outsides over here. Okay? All right. So I'm going to give you like 5 or 6 minutes to do this. Again, type done when you're done. If you have any questions about a specific one, I can try and guide you through it. But I'm going to let you get to work. We'll go over the answers in just a little bit. I feel like there's a lot of problems here, so if you need more time, let me know. Would 2 or 3 minutes be enough time? Let me know, or maybe you need more. Just say so in the chat. All right, 1 more minute. We'll go over the answers. All right, let's go over the answers. I gotta do some setup here. And, oh. We'll just slide that over. Okay. So I'm not going to write out the directions every time, like 1, count the electrons, etc. We're just going to verbally say them. So here's our first one, CS2. And so we're going to count the valence electrons. So carbon is in group 14. It has 4 electrons. Sulfur is in group 16. It has 6. There are 2 of them. And that gives me 16 electrons. Now you might notice, well, wait a second, this is looking awful lot like CO2, and all I'm doing is replacing O with S. It turns out, yeah, totally the same. All that matters is the number of electrons in determining your shape. So when I draw the framework here, yeah, it looks just like CO2, doesn't it? And when I do all the steps, it'll end up with the same result because there were 16 electrons. So I'm going to put my outer electrons first, 2, 4, 6, 8, 10, 12, and then the 2 lines were 14, 16. So I've used all my electrons. I don't have an octet, so I need to remove some of the electrons off the sides to make multiple bonds. And there you go. So there's CS2. All right, let's do PCl3, and I'll do it a little more slowly because this one will be different. So phosphorus is in group 15. It has 5 valence electrons. Chlorine has 7 valence electrons because it's in group 17. There are 3 of them. 21 plus 5 is 26. Hey, this one does not have a multiple of 8. But it still works. We can still do it. So I'm going to make my central atom phosphorus, because it was written first. Then I'll connect the rest for my framework. And so that's 6 electrons. So now I have 20 left. I'm going to put electrons around the outside. 1, 2, 3, 4, 5, 6. That one was a little tiny. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And the last 2 go on the central atom, and then everything has an octet. So there's your structure. All right, now we've got SiCl4. Silicon is in group 4, so it has, or group 14, sorry, so it has 4 valence electrons. Chlorine is still in group 17, so it has 7 valence electrons. There are 4 of them this time, for a total of 32. For my framework, I'm just going to put silicon in the middle and go Cl, 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 Cl. 1, 2, 3, 4 bonds. That's 8 electrons. And I'm going to put dots around the outer ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Look at that. Works out just perfectly. And there's your structure. With CH2O, it looks like it should be more complicated because there are more atoms involved, right? But we'll follow the same rules. Carbon's in group 14, it still has 4. Hydrogen's in group 1. There are 2 of those. And then oxygen is in group 16. It has 6. 4 plus 1 times 2 is 6, plus 6 is 12. All right, I'm going to do my framework. Carbon goes in the middle, and then everything else on the outside. Doesn't matter where you put them, because you can spin it around. 2, 4, 6 for my framework. And then I only can put electrons on oxygen, because hydrogens are done. They only accept 2. So 1, 2, 3, 4, 5, 6. So all my electrons are done. I don't have an octet on carbon, though. Carbon only has 6 electrons around it, right? It's only got 3 lines. So I have to invoke step 5 and make multiple bonds. Oh, hi. There's a cat here. Hi. Meow. Do you want to say hi? Meow? He doesn't want to say hi. He's shy. Say hi. No. Okay. So there's the first 4. I'll let you copy that down if you need to, because then I got to scroll the page up and erase everything and start at the top again. All right, so pause the video if you need to. All right, so let's try some of these with multiple central atoms. So again, carbon has 4. There are 2 of them. Fluorine has 7. It's in group 17. There are 2 of those. So I have 8 plus 14 is 22. Oh, you're so soft. My cat is trying to rub my arm while I'm writing. No, you can't be in my lap right now. I'm working. You gotta move. Oh, don't get stuck. Got caught on the headset. My cat's not going to take no for an answer. I'm just going to ignore him. All right. Carbon is the central atom. We're going to just stick those 2 stuck together, and then I'm going to put the fluorines on the outside. A general strategy for this sort of thing is to distribute them as evenly as you can. So I'm going to have something that looks kind of like this when I'm done. All right, now I'm going to put electrons around the outside atoms first. So 1, 2, 3, 4, 5, 6. Oh, wait, hold on, sorry. I put down 3 lines, so I got to do this. All right, now I can do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I have 4 electrons left for the central atoms. And I'm just going to do this, because that gives everything an octet. Or that gives something an octet, I should say. This carbon, however, right here, this one doesn't have an octet. So we need to fix that. Now, you have a choice here. And one of the choices is going to be more consistent with the rules that we've talked about so far than the others. So I could do... What I'm going to do is I'm going to copy this. Oops, hold on. We're going to copy that and paste it down here. So we have 2 options here. So I could erase these. Oops, I'm on the wrong layer. Hold on. Merge down. There we go. I could move these and do this. Or I could do something like this. Maybe not that one. Hold on. Which one is correct? Because in the bottom structure, everything has an octet, right? But remember what we said about how many bonds things like to make, right? Remember that the rule was 8 minus group number we want to make 8 minus group number, the ones digit, again, for the group number, bonds on an atom. So carbon is in group 14, so the ones digit is 4, so carbon should do 8 minus 4 equals 4 bonds, right? And fluorine should do 1 bond. So which structure is the better one? Well, up here, my carbons have made 4 bonds and my fluorines have made 1. So this is good. But down here, fluorine made 3 bonds. That's no good. And then this carbon only made 2 bonds instead of 4. That's also no good. So this structure is not correct. Okay, so don't forget that there is a guide to the number of bonds that each atom should make for these structures that you're going to see. Okay, so if you get to a place where it's like, oh, I have a choice, where do I put the extra bonds? Whose electrons do I use? Remember the guidelines over here for how many bonds things make. Okay, and that'll clue you in onto which one you should do. All right, let's go to the next one. Let's do C2H6. So there's my carbon. Hydrogen gives you 1 electron, and there are 6 of them. So this is 8 plus 6 is 14. And so we'll put our carbons in the center, and I'm going to put a bunch of H's around the outside. We're going to try and do it as equally as possible. So 3 on each side. So 1, 2, 3, 4, 5, 6, 7, counting the central bond, total bonds. Look at that. That's the Lewis structure for C2H6. You're all done. Way easier than doing connect the dots, right? Way less tedious, anyway. And then finally, for this one, CNBr. Add up all my electrons. Carbon goes in the middle. Nitrogen on the one side, Br on the other. So 2, 4 for my framework. And then I'll go 2, 4, 6, 8, 10, 12. And then again, it's which side do I make the multiple bonds to? Well, remember, elements in group 7, this bromine over here only wants to make 1 bond. Nitrogen wants to make 3 bonds. So I'm going to just take both of them from nitrogen here. So go boop, boop. And there's the answer. All right, I hope that was helpful. That's how you draw Lewis structures, and that's as far as we're going to do Lewis structures in this class. So that was Unit 10. That is everything that you need to know about Lewis structures for Chem 140. So if you have any questions, let me know. So let me turn the sound up so you get your hooray here. Yay. All right. So that's going to be a quiz posted to Canvas for Units 9 and 10. I have to close these slides real quick so I can open the next ones. We're going to do a little bit of Unit 11 today. Just a little bit. We'll do most of it tomorrow. Because we have some time left. All right. Unit 11 is all about naming. We've been mentioning a bunch of compounds just sort of by their formula. We've drawn pictures of them. We've referred to them. Now we're going to start formally naming things. Now, in order to name compounds, you first need to identify what category the compound in question is. So the first section here is going to be categorizing compounds into one of these 3 categories below. Ionic, molecular, or acid. You've already seen these 2. This third one is a new one, and we're going to introduce it in this section. And then we're never going to talk about acids again until 163, in which case we're going to talk about them like crazy. But we are going to use them, and so when you're in the laboratory, hopefully next quarter, and the directions say, go grab the hydrochloric acid, you'll know what that is. You'll be able to do that because you'll see it on the bottle. So that's our first step. We're going to first put things in categories, and then we're going to use specific rules to name stuff. Now, the naming chapter it's not long, but it is very important, and it actually has its own quiz. So when we're done with this tomorrow, another quiz will go online. So that means that there's going to be 2 quizzes due next week. Be mindful of that, and make sure you do them ahead of time. Don't just let them pile up, okay? All right. So let's talk about nomenclature. Nomenclature is just the rules for naming. Now, each category that we're going to talk about, these 3 categories right here with the red arrows, has its own set of rules. So this first step is going to be very important. If you use the wrong rules because you categorize the molecule wrong, you get the wrong result. So be very, very mindful of that. Make sure you are using the correct rule set because you categorize the molecule correctly. Okay? So the first step to naming something is going to be this. What rules do I use? What category does it belong to? Now, these 2 categories right here are the same category. These are going to be our ionic compounds. This is going to be, actually, what I'll do is I'll just label it this way. If I could pick the pen, there we go. That's going to be section 11.2. This one's going to be section 11.3. This one's going to be 11.4. All right. The way that we're going to name compounds is that they will fall into one of these categories on the screen here. The first category is binary ionic compounds. So what that means is that it's an ionic compound, and there is a metal and a nonmetal element, and that there are only 2 elements. That's what binary means, is 2. Polyatomic ionic compounds will just have a polyatomic ion. This is where the naming chart at the start of Unit 6, so remember that the polyatomic ions are on the slides at the start of Unit 6. That's where I gave you that list and asked you to try and commit them to memory. Hopefully you've looked at it at least and have started to, recognize them. Down here for molecular compounds, again, it's binary for our naming. We're only going to name binary things, so you're not going to name something like CH2O. You're just going to name C2H4, and so on. Binary molecular compounds have 2 nonmetals. And then we have this last one, which is the special one. We've got acids here. Acids start with H in their formula. Now, not all things that start with H are considered to be acids. For instance, water. Water's kind of weird. Water is actually, by definition, the weakest acid. If you are less acidic than water, you are not an acid, you're a base. But we're not going to name water following the acid rules. We're going to name it following the covalent rules. So there are some rare exceptions based on the definition of acids, which we'll talk more about in 163. But all other things that aren't water will follow these rules. And so that's your goal, is to look at the formula and say, okay, what's in there? What is it? So let's do that. So first of all, let's find the binary ionic compound. So binary ionic, or it could be polyatomic. Or binary covalent. Or acid. So let's look at these. First, let's look for the binary ionic compounds. Remember that anything that has a metal and a nonmetal is binary ionic. So let's look for metals. Oh, there's a metal. Does it contain a nonmetal? It does. So this one is binary ionic. Cool. All right, let's look for binary covalent, which would be 2 nonmetals. So, well, they both contain nonmetals, but only one of them contains 2. This one contains like a ton of them, right? Also, this one up here starts with H. So we're going to categorize that as a different thing later. That's going to be our acid. So this is our binary covalent. And then this last one here, which I guess I'll do in green, starts with H. It's our acid. All right, there you go. That's all you have to do. You just have to categorize the compounds. All right, so this is something you can do in the chat. Oops, I didn't mean to go to the next slide. So type it in for each of these, which category it goes into. So I'll number them for you. That's not how we number. I don't know why I did that. So what is HCl? It could be binary covalent. We're going to name it like it's an acid, though. So think of the acid as, since it's its own category, if something qualifies as an acid, treat it as such. So yeah, HCl would be an acid, because we wrote H first. That's actually a good question. It is both, right? Now, remember, water is the only exception. Water we're going to name as a covalent. All right. Go ahead and categorize these. I'll give you like 2 minutes to do it because this is pretty straightforward. And then we're done. We'll start actually naming stuff tomorrow. Okay, see you in a bit. So I'm going to go over the answers because we're going to run out of time. But remember, for binary ionic, we want to find all the metals paired with nonmetals. Does the H have to be at the beginning to be an acid? Yes. So if the H is in the back somewhere, not an acid, it has to start with H. So I'm going to underline in green here all the metals. And so these will be, so 1, 4, and 7 are binary ionic. And then we need to find the polyatomic ones. That's this one right here. Because it's got an ammonium and a phosphate. You're going to see the polyatomic ions all over the place, but if you have only polyatomic ions in there, or sorry, not only polyatomic ions. If you see a polyatomic ion for the metal, such as ammonium, that counts as polyatomic ion. Polyatomic ions tend to want to pair with acids a lot of the time, so you're going to see them like right here. This one starts with an H, this one starts as an H. So 2 and 6 are going to be acids. And then the other ones must contain only nonmetals. There you go. That should be all of them, right? Yeah. All right, so make sure that you are looking at those a little bit before we go to lecture tomorrow. For tomorrow's lecture, do look over the naming rules just briefly. They're going to be a little bit involved, and if you've seen them before, then our discussion gets a little bit easier. So I definitely recommend that you at least look over the slides maybe tonight before we do that all tomorrow. I do want to thank everybody for coming out to the lecture. Tomorrow we will do Unit 11. We will probably complete Unit 11. If we don't finish Unit 11 on Tuesday, I'm going to use a little bit of Wednesday to do it because there's no lab being assigned this week. So we'll finish it up on Wednesday. And then we'll have our Q&A. At the end of this week, we end the section of the class that does not use math. So starting in week 8, we're going to go back to math all the time. So make sure you have your calculator handy and be mentally prepared for all of the dimensional analysis that we're going to be doing. We're going to be doing a lot of it for the rest of the quarter. Yeah, that's really all I have. So have a wonderful rest of your evening. I'll see you tomorrow, and happy November.